examine this topology. What do you see? You see the distribution layer switches, DSW1 and DSW2. You see an access layer switch, ASW. And we have our client down at the bottom of the screen. Where would the root bridge be, typically? Well, by default, the root bridge would be elected based on the switch having the lowest bridge ID. And if it wasn't one of the distribution layer switches, more than likely, you modified the priority. So that way there, DSW1 as an example, could become the root bridge. And the reason why you did this was to optimize traffic flow. You want traffic flowing from our PCs, out through the access layer, out through the distribution layer. You don't want to have traffic at the distribution layer having to come to the access layer only to be sent back up to the distribution layer, causing suboptimal layer 2 traffic flow. So more than likely you spent some time analyzing the most appropriate place to put the root bridge, and you made that happen by modifying the priority of DSW1. As a result, our topology would have designated ports here, root port here, designated port here, and a blocking port right there. Do we ever want ASW1 to be the root bridge in this case? No, we don't. Never, ever, ever. So if by accident somebody changes the priority, or maybe for malicious purposes, someone changes the priority, and that priority ends up being better than DSW1 or DSW2, then ASW1 is going to send out BPUs that state it is the best option for being the root bridge. And as a result, our topology would then look like this. Which means that the link at the distribution layer is no longer being used. And typically the link at the distribution layer between the distribution layer switches is a relatively fast link. And it's used for high availability, redundancy purposes. And here we are blocking it. We're not even using it. Not only that, but the access layer switch, the lower end switch in our topology, is now the root bridge for the spanning tree topologies. And we have suboptimal traffic flow as traffic has to flow through the root bridge. So how do we protect our root bridge placement? And how do we ensure that certain switches under any circumstances should never, ever, ever become our spanning tree protocol root bridge? Well, we can use a feature known as root guard. So root guard is another stability mechanism for spanning tree protocol, and it's designed to limit which switches within the topology can become the root bridge. And we can accomplish this by configuring root guard on those ports in the topology where the root bridge is never anticipated. So what do we mean by that? Well, let's examine DSW1's interface Ethernet 0/0. When you look at Ethernet 0/0, should we ever find the root bridge out that interface? No, we shouldn't. Let's examine Ethernet 0/0 on DSW2. Should we ever find the root bridge out that interface? No, because if we do, then the spanning tree topology is going to end up ultimately blocking this particular link right here. And we don't want that link blocked in our topology. We want to use it. So we will configure root guard on those interfaces where you will never have a root port. Think about it. If these interfaces are pointing to the root bridge, they would have to be root ports. So these interfaces right now are designated ports. That's what they are. So the goal of root guard is to make sure that these interfaces remain as designated ports and they don't become root ports because some rogue device or some legitimate device sending rogue BPDUs is saying I'm superior and I should become the root bridge. So we can configure root guard on the interface with the spanning tree guard root command. So this is a feature that is enabled on an interface by interface basis to maintain the stability of spanning tree protocol. So let's examine that right now on our distribution layer switches. If we look at DSW1, we'll see that DSW1 is the spanning tree root bridge for VLAN 10. This bridge is the root. These are our designated ports. DSW2 is going to be the secondary root bridge. So if DSW1 fails, we want DSW2 to become the root bridge for VLAN 10. And we want to make sure that ASW1 never, ever, ever, ever becomes the root bridge for the VLAN 10 or any other VLAN. So what we're going to do here is we're going to configure root guard on gigabit 101, 102 for both DSW1 and DSW2. So we can do interface range, gigabit Ethernet 1/0/1-2, and we can say spanning tree guard root. And we'll do the same thing on DSW2. And we'll go configure terminal, interface range, gigabit Ethernet 1/0/1-2, spanning tree guard root. All right, let's go back to DSW1. And we can see from our syslog messages that root guard was enabled on both gigabit 1/0/1 and 1/0/2. And we can verify this by looking at the output of show run pipe or show run interface gigabit Ethernet 1/0/1. So spanning tree guard root has been enabled for gigabit 101. And if we go to 102, we can see spanning tree guard root has been enabled there as well. But let's not forget about our spanning tree command. So show spanning tree interface gigabit Ethernet 1/0/1 detail. By looking at this output, we can see on gigabit 101 that root guard is enabled on this particular port for VLAN 1. It's enabled for VLAN 10. It is enabled for VLAN 20, enabled for VLAN 99, enabled for VLAN 100, and it's enabled for VLAN 200.